Welcome to this coding walkthrough. Today, we'll explore problem number 243, shortest word distance. This problem is a great opportunity to sharpen your skills in string manipulation, indexing, and efficient algorithms. Let's dive in and understand how to solve it step by step. In this problem, you're given an array of strings called wordsdict in two distinct words, word 1 and word 2. Your goal is to determine the shortest distance between the indices of these two words in the array. The distance is calculated as the absolute difference between their indices. For the input, you'll receive wordsdict, which is a list of strings, and two separate strings, word 1 and word 2. In terms of output, you need to return an integer representing the shortest distance. For example, if wordsdict contains the words practice, makes, perfect, coding, makes, and you're looking for the distance between coding and practice, you'll calculate the shortest difference between their positions in the list. For the first example, the input wordsdict contains the words practice, makes, perfect, coding, makes, with word 1 as coding and word 2 as practice. The output is 3. This is because the index of coding is 3, and the index of practice is 0. The absolute difference between these indices is a 3 is 0, which equals 3. In another example, if word 1 is makes and word 2 is coding, the output is 1. Here, the closest occurrence of makes is at index 4, and coding is at index 3. The shortest distance, therefore, is a fourth 3, which equals 1. Now, take a look at the third example, where wordsdict is a, b, c, d, a, c, b, a, and you're finding the distance between a and b. The output is 1. The first occurrence of a is at index 0, and the first occurrence of b is at index 1. The absolute difference between these indices is 1 and 0, which equals 1. Even though there are other instances of a and b in the list, the shortest distance remains 1. This highlights the importance of finding the closest occurrences of the two words, regardless of how many times they appear in the array. There are a few constraints and edge cases to consider for this problem. The length of wordsdict will be between 2 and 10,000, and each word in the list will have a length of up to 10 characters. The words consist only of lowercase English letters, and word 1 and word 2 are guaranteed to be different from each other and will always exist in wordsdict. For edge cases, think about scenarios like when wordsdict has the minimum length of 2, such as a, b, where word 1 is at and word 2 is b. Another situation is when word 1 and word 2 appear multiple times in the list. Your solution must ensure it finds the shortest distance, even with repeated occurrences. For example, if wordsdict is a, b, the algorithm must correctly compute the shortest distance between a and b. To tackle these cases efficiently, the solution should ideally run in O(n) time complexity, where n is the length of wordsdict. To start, we can consider the brute force approach. This method is straightforward and relies on iterating through all possible pairs of indices in the array. The goal here is to find every occurrence of the two target words, word 1 and word 2, and then calculate the absolute difference between their indices. By doing this for all pairs, we can determine the smallest difference. The steps are simple: use two nested loops to locate all the indices for both words, compute the absolute difference for each pair, and keep track of the minimum difference. While this approach is easy to implement and conceptually simple, it comes with a major drawback: its inefficiency. The time complexity is quadratic, O(n) squared, because of the nested loops, which makes this approach infeasible for large input sizes. However, it does have the advantage of not requiring additional space beyond the variables used to track the minimum difference. This trade-off highlights that while the brute force approach is accessible, it struggles with scalability as input size grows. Now, let's consider a more efficient approach that addresses the scalability issue. The optimized method uses two pointers to track the most recent indices of word 1 and word 2. Instead of comparing all possible pairs, we only focus on the most recent occurrences of the two words, which eliminates unnecessary calculations. The process begins by initializing two variables, index 1 and index 2, to -1. These variables will store the latest indices of word 1 and word 2 as we iterate through the array. Whenever we encounter one of the target words, we update the corresponding pointer. If both pointers are valid, that is, neither is still at its initial value of -1, we compute the absolute difference between them and update the minimum distance. This approach ensures that we only make a single pass through the array, achieving a linear time complexity of O(n). Additionally, it maintains constant space complexity as we use only 2 extra variables. While slightly more complex to implement than the brute force method, this approach is highly efficient for large inputs, making it a powerful alternative. The optimized approach stands out as the ideal strategy for solving this problem. By reducing the runtime from quadratic to linear, it becomes highly effective for handling large input sizes. At the same time, it maintains simplicity by requiring only a small amount of additional space. The core insight that makes this approach work is the realization that we can dynamically track the most recent indices of word 1 and word 2 using 2 pointers. This sequential traversal avoids redundant comparisons and allows us to focus only on the necessary calculations. By combining efficiency and clarity, the optimized solution strikes a balance between performance and ease of implementation. This makes it the best choice for solving the shortest word distance problem both effectively and elegantly. To start, the problem asks us to calculate the shortest distance between 2 words in a list called wordsdict. Specifically, you are given 2 words, word 1 and word 2, and the task is to find the smallest difference between their indices in this list. First, let's look at the brute force approach. In this method, we initialize a variable min_distance to infinity, which will store the smallest distance we find. Then, we use 2 nested loops to examine all possible pairs of indices. This means for each index I where word 1 is found, we compare it to every index j where word 2 is found, calculating the absolute difference between these indices. While this approach is straightforward, it can become computationally expensive due to the nested looping over all possible pairs. Next, we refine the brute force approach by checking for matches during the nested iteration. For each index I, we verify if the worded wordsdict, I, matches word 1. Similarly, for each index j, we check if wordsdict, j, matches word 2. When both conditions are satisfied, we calculate the absolute difference between I and j. If this difference is smaller than the current min_distance, we update min_distance to this new value. Once all pairs have been evaluated, the value of min_distance is returned as the result. However, this approach still involves examining all pairs of indices, which is inefficient. To address this, we can use an optimized method called the 2-pointer technique. In this approach, we initialize 2 variables, index 1 and index 2, to -1. These variables will track the most recent indices where word 1 and word 2 are found. We also initialize min_distance to infinity, as before. Now, we optimize the solution with a single pass through the list. Using a single loop, we iterate through the list wordsdict with an index I. During this traversal, if the worded wordsdict, I, matches word 1, we update index 1 to the current value of I. Similarly, if the word matches word 2, we update index 2 to I. At every step where both index 1 and index 2 are not -1, we calculate the absolute difference between these 2 indices. If this difference is smaller than min_distance, we update min_distance to reflect this new distance. Once the loop is complete, the final value of min_distance is returned. This approach is far more efficient because we only traverse the list once, reducing the number of comparisons significantly. The key insight here is the inefficiency of the brute force approach, which has a time complexity of O(n²) due to the nested loops. This becomes impractical for large lists. In contrast, the 2-pointer technique reduces the time complexity to O(n) by processing the list in a single pass and focusing only on the indices of interest. Additionally, the space complexity is O(1), because we use a few integer variables to track indices and the minimum distance. The algorithm is robust enough to handle edge cases, such as when one or both words are missing from the list, by returning an appropriate result like -1. It also handles duplicate occurrences of words by always updating the latest index, ensuring that the shortest distance is computed. To solidify our understanding, let's walk through an example. Suppose the input list is wordsdict equals practice, makes, perfect, coding, makes, with word 1 equals coding and word 2 equals practice. Initially, we set index 1 and index 2 to -1, and min_distance to infinity. As we loop through the list, at I equals 0, we find practice and update index 2 to 0. At I equals 1 and I equals 2, we don't find any matches, so no updates are made. At I equals 3, we find coding and update index 1 to 3. Now, both index 1 and index 2 are valid, so we calculate the distance, abs, 3 to 0, equals 3. Since this is smaller than infinity, we update min_distance to 3. At I equals 4, no changes occur. Finally, the shortest distance is 3, which is returned as the output. Finally, let's analyze the complexity of our optimized approach. The time complexity is O(n), as we only traverse the list once. This is a significant improvement over the brute force approach, which has a time complexity of O(n squared). The space complexity remains O(1), because we do not use any additional data structures, only a few integer variables to track indices and the minimum distance. This makes the two-pointer approach both time-efficient and space-efficient, making it well-suited for large input lists. This implementation solves the problem of finding the shortest distance between two words in a list in an efficient manner. The function shortest distance takes in three parameters: wordsdict, which is the list of words, and word1 and word2, the two words whose shortest distance we want to calculate. We start by initializing two variables, index1 and index2, to -1. These variables will keep track of the most recent indices where word1 and word2 were found. We also initialize min_distance to infinity, as we want to minimize this value as we process the list. Next, we iterate through the list wordsdict using a for loop with enumerate. This gives us both the index, I, and the word at each position. If the current word matches word1, we update index 1 to the current index. Similarly, if the current word matches word2, we update index 2. After updating either index 1 or index 2, we check if both indices are valid, i.e., not -1. If they are, we calculate the absolute difference between the two indices and update min_distance if the new distance is smaller. Finally, after processing the entire list, we return min_distance, which contains the shortest distance between the two words. This approach is efficient, as it only requires a single pass through the list, resulting in a time complexity of O(n), where n is the length of wordsdict. The space complexity is O(1), since we only use a constant amount of extra space. This is the Java implementation for LeetCode problem number 243, shortest word distance. The logic mirrors the Python solution, using a single loop to track the most recent indices of the two words, and updating the minimum distance whenever both indices are valid. Key differences include explicit type declarations for variables, the use of Java's math.min for calculating the minimum, and the array-based approach with string, for the input list of words. The code is concise and follows Java conventions, ensuring clarity and efficiency. To solve this problem, let's start by looking at an example. Here, the input array is a list of words, wordsdict, and we want to find the shortest distance between the words coding and practice. We begin by initializing three variables, index1 and index2 to -1, which will store the most recent positions of coding and practice respectively, and min_distance to infinity, which will track the smallest distance we find. Now, as we iterate through the list, we start with the first word at index 0, which is practice. Since it matches word2, we update index 2 to 0. However, since index 1 is still -1, we can't compute a distance yet. Moving to the second word, makes, it doesn't match either word1 or word2, so we simply continue without making any updates. Next, we encounter the word perfect at index 2, which again doesn't match either word1 or word2, so we move on. At index 3, we find the word coding. This matches word1, so we update index 1 to 3. Now that both index 1 and index 2 have valid values, we calculate the distance as the absolute difference between the two indices, abs, 3 to 0, which equals 3. We then update min_distance to 3. Finally, at index 4, we see the word makes again, which doesn't match either target word, so no further updates are needed. The shortest distance between coding and practice in this example is therefore 3. Now, let's consider a second example where the same target words appear at different positions. In this example, we want to find the shortest distance between the words A and B in the list. As before, we start by initializing index 1, index 2, and min_distance. At index 0, the word is A, so we update index 1 to 0. Since index 2 hasn't been updated yet, we can't calculate the distance. At index 1, the word is B, so we update index 2 to 1. Now that both indices are valid, we calculate the distance as abs, 1 to 0, which equals 1. This becomes our new min_distance. At index 2, the word is C, which matches neither target word, so we move on without making any changes. At index 3, we find it again, so we update index 1 to 3. With both indices valid, we calculate the distance as abs, 3 to 1, which equals 2. However, since our current min_distance is already 1, we don't update it. At index 4, we encounter B again and update index 2 to 4. The distance between these indices is abs, 4 to 3, which equals 1, so min_distance remains 1. The shortest distance between at and B in this case is 1. Now, let's look at a third example where the target words are consecutive in the list. In this third example, we are searching for the shortest distance between the words Y and Z. As always, we begin by initializing index 1, index 2, and min_distance. At index 0, the word is X, which doesn't match either target word, so no updates are made. At index 1, we find Y, which matches word 1, so we update index 1 to 1. Since index 2 is still -1, no distance is calculated. At index 2, we encounter Z, which matches word 2, so we update index 2 to 2. Both indices are now valid, so we calculate the distance as abs, 2 to 1, which equals 1. We update min_distance to 1 as this is the smallest distance we've seen so far. At index 3, the word is X, which doesn't match either target word, so we continue without updates. At index 4, we find Y again, so we update index 1 to 4. Both indices are valid, so we calculate the distance as abs, 4 to 2, which equals 2. However, min_distance remains 1 because it's already the smallest value. Thus, the shortest distance between Y and Z in this example is 1. This concludes our walkthrough of the solution for finding the shortest word distance between two given words in an array. To analyze the time complexity of the solution, we start by looking at the operations performed within the loop. The algorithm iterates through the wordstick list exactly once, processing each word in sequence. For each word, it checks if the current word matches either word 1 or word 2, which are constant time operations, or O1. If there's a match, it updates the respective index, another constant time operation. Then, it verifies if both indices are valid and calculates the absolute difference between them, which is also done in constant time. Finally, it uses the min function to update the minimum distance, an operation that is again constant time. Since all these operations are O1, and the loop runs n times for a list of n words, the total time complexity is the product of these n iterations and the constant time operations within each iteration, resulting in an overall time complexity of O(n). Now, let's examine the space complexity of this algorithm. The solution only uses 3 integer variables, index 1, index 2, and min_distance. Each of these variables requires a fixed amount of memory, or constant space, which is denoted as O1. Importantly, the algorithm doesn't use any additional data structures like lists or dictionaries, and it accesses the input wordstick in a read-only manner without modifying it. This means the memory usage does not scale with the size of the input, and the total space complexity is therefore O1. Next, we consider the best, average, and worst-case scenarios for this solution. In the best case, the indices of word 1 and word 2 are identified early in the list. However, the algorithm still needs to iterate through the entire wordstick to ensure there are no shorter distances, so the time complexity remains O(n). In the average case, the algorithm processes all n elements, performing constant time operations for each, which again leads to O(n) time. For the worst case, where word 1 and word 2 are positioned at opposite ends of the list, the algorithm must still traverse all n elements, retaining a time complexity of O(n). When compared to the brute force approach, which involves 2 nested loops to find and compare all possible index pairs, the naive solution results in a time complexity of O(n²). In contrast, the optimized solution achieves O(n) time by using a single pass through the list, while both approaches maintain a space complexity of O1. Finally, let's mathematically validate the big O analysis. If n represents the number of elements in wordstick, the solution performs one iteration over all n elements. Within each iteration, it executes a constant number of operations, such as comparisons, updates, and calculations. This gives us a total number of operations equal to n*O1, which simplifies to O(n). Furthermore, since the algorithm does not allocate any additional memory beyond the 3 integer variables used, the space usage remains constant at O(1). These calculations confirm that the solution is both time-efficient and space-optimal for solving this problem. One common mistake beginners make is using an inefficient brute force implementation. For example, they might use nested loops to check all pairs of indices for word 1 and word 2, resulting in O(n²) time complexity. This becomes impractical when working with large input sizes. Instead, you should aim to optimize using techniques like the two-pointer approach or by pre-computing the indices of the words you're searching for. Another frequent issue is misinterpreting the problem statement. It's important to carefully read the requirements, as some might assume the words are unique or not consider multiple occurrences of word 1 and word 2. Edge cases can also be tricky. If either word 1 or word 2 doesn't exist in the list, it can lead to runtime errors. Always validate your input and explicitly handle such scenarios. Additionally, many solutions become overcomplicated due to unnecessary data structures, like creating multiple lists or maps, which can increase memory usage. Strive to write solutions with minimal overhead. Finally, pay attention to whether the problem is order sensitive. If, for example, the question requires word 1 to appear before word 2, failing to account for this detail could result in incorrect outputs. Now, when approaching this problem in an interview, there are a few key insights to keep in mind. First, make sure you fully understand the input and output requirements. For example, clarify how to handle duplicate words, empty inputs, or situations where word 1 and word 2 are the same. Next, always discuss the trade-offs between time-efficient and memory-efficient solutions. Interviewers often value when you can articulate thoughtful reasoning behind your approach. It's also a good idea to start with a brute force solution, highlighting its limitations, and then incrementally optimize. This demonstrates your ability to refine and improve your approach. Speaking of optimization, the two-pointer technique is a great way to minimize the distance between indices efficiently, and it's worth discussing during the interview. Lastly, be prepared to compare alternatives. For instance, explain why a particular approach is more suitable given the constraints, such as the input size or the frequency of queries. This not only shows your technical skills but also your ability to evaluate solutions critically. There are also several related problems that can help you deepen your understanding of this topic. For example, LeetCode 243, shortest word distance, is a simpler version of this problem where you find the minimum distance between two words in a list. LeetCode 244, shortest word distance 2, introduces multiple queries, requiring you to think about efficient pre-processing strategies. Then there's LeetCode 245, shortest word distance 3, which is a variation where word 1 and word 2 can be the same, adding another layer of complexity. Beyond these, LeetCode 532, kdiff pairs in an array, shifts focus to finding pairs with a specific difference, which requires careful handling of both indices and values. To solve these problems, you can also explore alternative approaches. For instance, the hash map approach involves pre-computing the indices of all occurrences of word 1 and word 2, allowing you to use two pointers to minimize the distance efficiently. However, this increases the space complexity. For dynamic updates in real-time scenarios, a sliding window approach works well, especially for streaming data. Another option is binary search. If the indices for word 1 and word 2 are pre-computed and sorted, you can use binary search to quickly find the closest pair, which is efficient for repeated queries. Each of these approaches has its own trade-offs, so it's crucial to choose the one that best fits the constraints and input size of the problem you're solving. Great work! In this session, we covered the shortest word distance problem, discussed its optimal solution, and reviewed key takeaways for your coding journey. Remember, practice is the key to mastering these concepts. Thanks for your time, and I'll see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!